Let's also have a further look of a flocking model with geometric distance. This is suppose that this ice, the position of the ice agent, the radius r, that can be regarded as agent's neighborhood. So alignment means steer towards the average heading of its neighbors. So this is a agent. This its neighbors. Okay. I would like to mention the paper, the well-known paper, very popular paper by the Wiksek and his colleagues, Physical Review Letters in 1995. And he used this kind of model to investigate some properties in non-equilibrium systems, like phase transition, transportation, and so on. So I would like to mention that this model is also a simplified Boyd model. A Boyd model for flocking behavior. I will mention this model at the end of my talk. Okay. Now, to pursue further, let us introduce some further notations. So this is a geometric distance. Neighbors defined as a geometric distance. It's ice agent's neighbor. Ice, as I mentioned before, the position of agent I in the plane. So and the theta I is the heading of agent I. V is the constant speed of agent. R the radius of the neighborhood. So we assume that a group of agents moving on the plane with a constant speed, and with radius denoted by R. So now you can arrive at a mathematical model. First one is the definition of the neighbor. So the heading is the average of the headings in his neighbors. So I belongs to J belongs to this neighbor. Summation of theta j's and in this neighborhood, and the position is updated by this heading, and so this. You can see the position and the heading are strongly coupled, and also nonlinear. Okay, because you can see theta I depend on ni, like this. Okay, and xi depend on theta I. Okay, theta I depend on ni. So ni, capital N depend on xi. So this is strongly coupled equation. Seemingly simple from a mathematical point of view. If you don't, investigate in some details, it may say, oh, wow, this is quite simple. However, if you consider it for some more time, you will see that's really non-trivial. Because there's local interactions and nonlinear dynamics. Now let's have a look of the phenomena provided in Wiksek's paper. Here is a simulation, very interesting. This is the initial at the initial stage. If you have a high density and a large noise in the model, then you can see the system will behave like this. It's quite like random walk, but with some correlation. However, if you have a small density and small noise like this, you can have some clustering phenomena. And then if you have high density and small noise, then you can have you can see some synchronization or consensus phenomena here. So this is the most interesting phenomena we are going to investigate. So the natural question is, can you establish a theory? Here is the some of the useful mathematical tools listed here, and most of the tools will be used in a study of this kind of problems. So before going further, let's have a look at the definition. I believe many of the audience, if not most, certainly know the definition about connectivity. So if there is a path connecting any two vertices of this graph, then we call this graph is connected. So joint connectivity is a joint of the graph. A union of the graph is a connected graph. Then it's a joint connectivity. So I would like to mention a seminal work in this direction. If we linearize heading, I will show you what's the original one. So it's a nonlinear equation. If you linearize just the heading equation, then you will get the first one, then the second one, the position equation is still there. And you will have this time-varying linear system. But it's still nonlinear because it's depend on this theta depends on this equation, and the P also contains Ni. Ni depends on Xi. Okay, so still a nonlinear equation. Anyway, this I would say this is a very interesting result. This result gets the best paper prize from IEEE transactions on automatic control. This result states that if the the system is jointly connected, the associated neighbor graph on the time interval is jointly connected with some edge, then you will have synchronization. Synchronization means all the heading converge for each agent converge to the same direction. So what's the problem? Okay, I will see. So as I mentioned before, the graph is defined by the position of the agent. Okay, the position is moved from time to time, so the graph will be changed. Will change from time to time. Okay, the graph depends on the position. The position and the heading depend, also closely related. Okay, so this simply means we assume that the position satisfies certain conditions. Okay, so that's a problem. So to see it again, the connectivity defined on the position. So this simply means in order to prove the synchronization of the flock, we need to assume a priori some assumptions on the trajectory of the system. Okay, so there are some related reference. Many, I would say, just a small portion of the existing studies was related problem in the literature. I would say most of the existing literature need a certain kind of a prior connectivity condition imposed on the dynamical behaviors of the multi-agent system to be studied. There are a few exceptions. I would particularly mention this paper by Cook and Smil in RI transaction TAC in 2007. This paper does not need connectivity assumption. But that's a different model. And the interactions among the agents are defined in another way. Okay, the interaction strength will be decaying with the distance between two agents. So each agent connected to any agent with a decaying strength. Okay, anyway.